So now we have our suitable uranium fuel, probably enriched. What do we do with it? Well, we need to design a reactor so that typically out of the 2 neutrons, the natural fission of every uranium-235 nucleus produces, at least one of them, and typically on average you want exactly one, triggers another fission. This means you get a steady chain reaction, not blowing up or shrinking away. That's quite tricky. I mean, if it's on average 1.1, then the reaction is going to get bigger and bigger and bigger and bigger. If it's 0.9, it'll fade away to nothing. So keeping the fraction of neutrons that actually go on to produce another fission at about 1 neutron for every fission is the goal of the reactor. So we need uranium-235, and it turns out that slower neutrons trigger more fission of uranium-235. This is basically because as they go past, they linger longer in the vicinity of the nucleus and so give more time to trigger the reaction. Here is the fission cross-section, which is how likely it is to produce a fission as a function of the energy, and you can see the lower energy, i.e. the slower neutrons, have much higher cross-section. So if you can slow the neutrons down enough, you don't need so much uranium-235 enrichment. This is done with moderators. A moderator is a substance because the neutrons that come out of uranium-235 fission are actually travelling very fast, and so what you need is to get them bouncing off a bunch of other nuclei, and in the process losing energy and slowing down, being called thermalized, converted to thermal energies. Now the best of these moderators is heavy water, that's deuterium, so it's water with H2O, but the H, at least one of them, is replaced by deuterium, which has the extra neutron. This is enough to get a chain reaction with unenriched uranium. And this is how the Canadian reactors work. The benefit is you don't need to enrich the uranium. The drawback is you do need to enrich the water. And maybe that's a bit easier because it's not so radioactive, but it's also a tricky process. But most reactors use normal water as a moderator. It's not good enough to get a chain reaction with the 0.7% uranium-235. You need to get the uranium-235 enriched up to about between 3 and 5%. So this is used by the vast majority of the commercial reactors around the world. Some reactors also use graphite, which is also a useful moderator. Okay, so now you've slowed the neutrons down enough that you're getting a self-sustaining chain reaction. That's going to release a lot of energy because as all the uranium nuclei fission, the fragments as they fly out dump kinetic energy and make everything very, very hot. Very, very hot, and if you're not very careful. So what you need to do is take the electricity away from the reactor and supply it to a turbine to generate electricity. And most reactors use water for this as well. It's a benefit of using water. It can act both as a moderator and as a coolant. It needs to be pressurized to give high temperatures though. I mean, if you just bring it up to the boiling point at 100 degrees, it's going to give you a low Carnot efficiency. So normally the water we put under enormous pressure so that it can boil at a much higher temperature so you can get more of the energy out. Other moderators, other coolants have also been used. The UK reactors for many years used air, actually, advanced gas-cooled reactors. And some reactors are talking about using liquid metals like liquid sodium. But water is the most widely used. And then finally you need control rods to keep the reaction just at the edge of being a chain reaction so it doesn't run away and melt everything or just fade away to nothing. So normally you have rods that you can lower into or withdraw from the reactor vessel made of material that absorbs neutrons. It slows down the chain reaction, and you'd adjust how far these are inserted to keep the chain reaction just chugging along at the edge of being a runaway to get you a decent amount of energy without getting too hot. Water reactors, pressurized water reactors in particular, also will often dissolve an absorbing material in the coolant, i.e. boric acid.